You're listening to the Australian Water Association podcast series. My name is Jo Taranto, and joining me is Dr. Michael Di Matteo. Michael is Senior Environmental Engineer at Water Technology, and we're discussing evaluating smart stormwater storage systems. Welcome, Michael.
Hi, Jo.
Urban stormwater management, it has a pretty big role in our growing cities. What are some of the challenges for a city like Adelaide?
Well, in a city like Adelaide, where we have a lot of infill development, so we're knocking down the old 1960s houses with big backyards and we're putting two houses in. What that does for stormwater, it increases the total volumes of water that run off into our streets, and especially it increases the intensity of the runoff when we have sort of our peak storm events as well. So our stormwater systems, they've been designed for the previous loadings, and now they're having to deal with these higher loadings and maintain their level of performance. So there's been also a need for increasing urban green spaces when we have urban infill development. So when we have these types of developments, we don't have the big backyards that we might have at one time. So we need green open spaces, and we need to keep those spaces watered to keep them lush and attractive.
So the project you've been involved in was a research collaboration. Can you tell us about who was involved?
Yes, so this was a research collaboration between university, local government, state government, and industry engineering consulting. So the University of Adelaide led the project, and it was co-funded with the City of Unley and City of Mitcham, so two inner city councils in Adelaide. And in addition, the state government, Adelaide and Mount Lofty Ranges Natural Resources Management Board. With these funding partners, Water Technology, which is where I came in, carried out some of the consulting services for the research project.
And tell us about what the aims of the project were.
So the main aim of the project was to investigate the benefits that smart stormwater systems can deliver when they're retrofitted into our urban environments. So Adelaide's looking at in the order of hundreds of millions of dollars necessary to install new stormwater systems or upgrade the capacity of our stormwater systems. And that's a large capital cost, and that's only targeted at the moment at maintaining the current level of flooding benefit in Adelaide. That level of funding through the traditional approaches, it's not addressing the urban greening and water quality improvement requirements as well. So this project, we were looking at how smart stormwater systems are able to deliver flooding benefits and also provide water for harvesting and urban greening, and what sort of cost-benefit trade-offs there are by using those smart systems.
And so what did you find about smart technology in stormwater rehab?
So when we use real-time control, we gain the ability to manage and control stormwater flows through our stormwater systems before and during a storm event. So we found that this has a really great impact on the performance of our stormwater systems, the ability to prepare for what's coming, and the ability to control the systems during real time. So we were able to achieve the same flood benefit that a traditional storage or pipe upgrade might achieve, but we were able to do it in a much smaller infrastructure footprint and a smaller cost. So by using our assets more efficiently, we're optimizing or sweating our assets by using real-time control technology.
And you used a few different options throughout that process to demonstrate that. What are some of the results that you saw with the different models?
Yeah, so we trialed several different scenarios. Our baseline scenario was a traditional pipe upgrade where we would rip up the existing pipes that are too small in the road and lay down larger pipes. We also looked at options for having a large detention storage at the end of our small urban catchment. And so there's not always space to actually fit those storages, but we took that storage size as a baseline approach. So those were our two traditional baseline markers, the pipe upgrade and the end of system storage. Then we had a look at can we get any efficiencies by distributing smaller detention storages throughout our stormwater network in the upstream network. And then going a step further, can we install real-time control to each of those storages in throughout the network? And so that would give us the ability to close the outlets of the storages and use them to store water throughout the year. So we could harvest water, use it for irrigation and urban greening. Or potentially, we also looked at can we operate those controls on each of the storage in real time during a peak storm event, and what type of benefit can we see if we took that real time control approach?
And is there a significant cost with this sort of smart technology, or is the benefit a no-brainer?
So we found that the results were really promising in terms of the cost effectiveness of using smart technologies compared with the traditional approaches. In particular, we found that using the smart outlets, smart controls in the stormwater network allowed us to manage flows in a way where we needed a lot less storage volume than we would have otherwise needed. So, for example, comparing our end of system detention storage with the distributed systems, we needed 40% less storage volume when you start distributing the storages. And another benefit of having distributed storages throughout the network means you don't have to put all of your upgrades within the main roads where they tend to be needed. You can have them occur in the smaller side streets, and that avoids the major disruptions to traffic as well. So the results of the study provide a good justification for researching these systems further because the cost benefit ratios are there.
It sounds like the benefits of a smart technology have been well validated by your research. Michael, what are some of the other results that you perhaps didn't expect or that have been shown to be positive?
Yeah, so we found that without any real-time control, that simply distributing smaller storages throughout the stormwater network was a more effective way per unit of storage to achieve your flooding target. So our end of system storage required 700 kilolitres of storage to achieve our flooding target, but with a distributed network of storages, we only needed 390 kilolitres, so a much smaller storage footprint. So if you're looking at going a step further and you have real-time control available for each of the storages, and you're able to control during a peak storm event, you can get a lot more benefit per unit of storage, and the required storage went down to 100 kilolitres to achieve your target. So from 700 kilolitres at your end of system storage down to only 100 kilolitres for your real-time controlled system. So it's quite a massive improvement per unit of storage when you're looking at distributing the storages first and then controlling those storages real-time in an optimal way.
Another area that you looked at was the role of machine learning and artificial intelligence. Can you tell us a bit about that?
So the main goal of using machine learning optimization approach in this research was to evaluate thousands and thousands of different system configurations and real-time control strategies for different storm events, to find the optimal system designs and their performance. So the optimization algorithm that we use finds designs that perform in an optimal way with the best flooding performance in the minimum storage footprint. So if you compare that with a traditional design approach where you have an engineer sitting there trialing different designs, the engineer might be able to come up with a dozen different designs. With the optimization approach, it lets you test hundreds and even hundreds of thousands of different designs in an automated way, especially when you combine it with the supercomputer used at the University of Adelaide. So the result is you're able to get a really good sense for the cost and benefit trade-offs for different stormwater system designs and control strategies. And the optimization approach was actually a key innovation from this study, and we've had an opportunity to use that approach on other projects.
You've said there's a real place for more research in this space. What are the other opportunities that exist?
So this was a modelling study. We were looking at whether there is a business case to investigate smart stormwater systems that deliver multiple benefits, investigate that further. So we've demonstrated that with the capital cost savings compared with a traditional pipe upgrade, that we could potentially have smart storage systems that would give you the same level of flooding benefit, but you can also provide water for urban greening and provide some water quality improvement as well. So the next step in the research is to trial an in-the-ground pilot system, and this would give us the ability to test real-world performance and how that matches in with the modelling results.
And I imagine there'd be interest from urban centres all over the world because this sort of information is relevant to their cities too.
So every city has its own unique issues, whether it's flooding or requiring water for urban greening. One of the benefits of using smart stormwater systems is that the same infrastructure can be used for multiple functions and benefits. So if you really want to maximize the utilization of the storage's flooding potential, you can do that by controlling the storage during a storm potentially. If you have a focus on urban greening, we found that you're able to harvest enough water to irrigate reserves and verges near the smart stormwater system, and using that same storage in non-peak times, so getting more utilization out of the same infrastructure. So there are multiple benefits that you can achieve by simply using smart stormwater systems.
It certainly sounds like there's some exciting opportunities ahead, Michael. I've been speaking with Michael Di Matteo. Michael is a senior environmental engineer at Water Technology. Thank you for your time.
Thanks, Joe.